Okay, let's start. So turn on video. Hi. So today I want to discuss the midterm exam first. Just I will briefly explain the questions, and then we continue the chapter 6, the linear regression. And if we have time, then hopefully we will do some exercises in slides. Okay. So So here is the homework, midterm questions. So it's due next Tuesday at 11:59. And the format is similar to homework 1 and 2. So we have some page limit and the size limit. So size limit is basically because of the grading convenience. And we have 4 questions. And the question 1, so household income for 900 families is available in the income.csv file. So this file is available in 2 formats in the midterm exam item in Canvas. And count the number of missing values systematically by using some function. And then they make a vector of household income which excludes all missing values, and make a histogram of that variable with breakpoints equal to 0, 10, 20, 30, up to whatever number which covers entire observations. And make a make a normal QQ plot for X and see if the distribution follow normal distribution. And the we make a QQ plot for different scale of X. Transformed version of X. So log of X, log means the natural logarithm, ln, and the X to the power 0.1, 0.2, 0.3, 0.4, and 0.6. So we have the 6 QQ plots and see if which one is the best in terms of normality. And of course, these transformations are very similar. So suppose that I choose this as the correct answer. Maybe your answer is this one or this one. But as long as you give reasonable explanation on your choice, then you should be fine. So even if they suppose that this is my correct answer, and if you choose this one, still it can be a correct answer, as long as your justification is correct. On the other hand, even if you choose the same answer as me, if you don't give any reasons, then probably you will not get full credits, maybe partial credits only. Any questions for question 1? You can, of course, ask questions later, but yeah. And question 2, the question 2 that we have observations, 7 observations. The weights of randomly selected 7 groundhogs in Pennsylvania are these. In pounds, maybe it doesn't have the unit, but it's pound. And let mu be the population mean weight of the groundhogs in Pennsylvania. So population is much larger, of course. And the test the null hypothesis against this. Originally, it has some typos. The H1 is mu is less than 10, so one-sided test at the 10% significance level. And explain the conclusion and its reason briefly. So it can be done in our language. And the next one, B. Okay, so B is the calculating the p-value of the test statistic in A, basically. But not based on the Qt function, but we want to use the random numbers to simulate the test statistic. Okay. So basically, under null hypothesis, that we calculate test statistic. So we can simulate it many times. So that is the question. So we want to calculate the p-value of the t statistic in A by simulation with only using the normal random numbers. So we have to basically evaluate the t distribution, but we are not allowed to use the t random numbers, but just the only normal random numbers. But the normal random numbers can create the t random numbers if we use some theorem, right? So we are not allowed to use these functions, but you can only use the R norm function. And yeah, so no functions about the random variables are allowed except for R norm function. You can use any deterministic functions not related to random variables. Yeah, then finally, they estimate the p-value of the test statistic in A by using the simulated results. So basically, we have to use the t distribution to calculate the p-value. Is which side, I don't know. But to calculate some area, one way is to calculate qt function, but another way is to using to simulate this distribution and empirically calculate the area. And here we have to empirically calculate the area using the random numbers. So that is question 2. Any questions? And question 3. Question 3 is about stock market. This is actual stock market data. Just I downloaded just before making question, so it's available from 2018 to 2023, October 12, 2023. And the sample size is 1,257. But usually we are interested in the stock return, not just the stock price. So stock return is defined by this. So this is almost similar to the change in ratio, like 0.01 or negative 0.01, but in more mathematically beautiful way. So not just percent change, but that we define log of xt minus log of xt minus 1 as basically the stock return. So based on xt, we can generate this. So since we have to take the difference, we only have 1,256 observations of YT. And YT is called daily return. So the number is like, I think the 0.01 or negative 0.02. It's almost similar to 1% change or negative 2% change, but we have the slightly different numbers. And the question B, extract all YTs whose previous day's return is in between negative 0.015 and negative 0.01. So the condition is here. So basically, we want to extract YT, but the condition is given by YT minus 1. Okay. So today's return is suppose the 1.2%, and the previous day's return is negative 1.1%. Maybe percent is a little bit confusing. So suppose the today's return YT, today's return is 0.015, and the yesterday's return is the negative 0.013. Then yesterday's return is in between these two numbers, so we extract this number. Okay. But if yesterday's return is negative yesterday's return is negative 0.013, but the return 2 days ago is positive 0.005, then this YT minus 1 does not satisfy this condition. So we do not take this one. Okay. So based on this criterion, we can extract YTs which satisfies this condition. Okay. So we extract yt's, but the condition is on yt minus 1. And for the observations, and yeah, so that is the B. And actually, to see if yt is extracted, we have to see the log of yt. So only candidates, we only have 1,255 candidates for yt. And some of them satisfy this condition. So basically, yesterday's return is between negative 1.5% and negative 1%. That is very specific conditions. So probably not many observations satisfies this condition. Maybe only 300 observations or 100 observations. I don't know, but not a very large number, we can guess. And C, for observations extracted in B, they calculate the percentage of positive daily returns. So we extracted some numbers, and some of them we don't extract. And based on extracted numbers, see if the yt is positive or not. And we can calculate the percentage of positive returns. Suppose in B, we extracted 300, and we have only 100 positive returns, then 100 over 300 is the answer. And D, by bootstrapping observations extracted in B, they simulate the percentage of positive daily returns for 1,000 times and make a histogram of the 1,000 results, and also calculate the 10th and 90th percentile of the distribution. So yeah, so out of these extracted numbers, 300 numbers, we bootstrap out of these 300 numbers. Out of extracted numbers, 300 is just the tentative number. You have to calculate in B, but the 300 observations with replacement. Then calculate again what percentage of observations is positive. Since this 300 is not exactly equal to this 300, maybe only 90 out of 300, or 95 out of 300, or maybe 108 out of 300 have positive return. Then we make distribution of this. So the idea is, if in C we have 0.333 as ratio, we only observe one ratio. So we want to evaluate how much variability this number has. And the bootstrap can identify it. So 0.333, but maybe, so if we make a distribution, so this 0.333 may not be very reliable estimate, and maybe this distribution ranges from 0.3 to 0.4 or something like that. So we want to do this. I got one question in chat. So can we use our own functions as long as they only use our norm? So as long as deterministic functions, you can use any functions in question 2b. Yeah. I think it's not realistic to make a function to generate random numbers, t random numbers, right? Don't use it. Yeah. In part C, another question I got from another student. In part C, how would there be any positive returns if part B only extracts negative returns? Yeah, so in question 3, conditions are on yt minus 1, but we extract yt's. Okay, so like this. So yt minus 1 is negative 0.013. So we extract y sub t, and y sub t can be positive. So that is the meaning of this question. Any other questions on problem 1, 2, 3? Okay, and question 4. This is more algorithmic question. So we want to develop a function to find a root of f of x by the Newton-Raphson method. It's just one root. So f of x may have multiple roots, but we only look for roots around some specific value. Yeah, if you don't know Newton-Raphson method at all, then you can read this page. It may help you to understand what we are doing. It's not really necessary for this specific question, but maybe it's good to see it. And basically, we want to create a function to find a root of f. And input is just f, and output is approximate root. And to be concrete, that we want to develop a following function. So initial value is 1/2. So basically, we are looking for a root of f of x around x is equal to 1/2. And if we have f okay, so 1/2 is here, x is here. We want to find basically this root. Then to do that, basically we calculate the f of 1/2, right? And then we consider the slope of this, right? And the slope of this. And then if we just extend the slope, then this is basically, approximate solution. So that is the idea of Newton-Raphson. This one, okay, so we have the y-axis and this value may be 15 or something. Then we go back the several steps and suppose the for example, the slope is 2. Slope is 2. Then basically we have to go back 7.5 to get approximate answer, right? So that is the Newton-Raphson method. So to do that, we have to calculate the derivative of f of x at 1/2. And the derivative, we are not doing mathematics, so we are doing a numerical computation. So we just approximate f prime of 1/2 as this with x is equal to 1/2. Then we update this one. So we start with x is equal to 1/2, but the next one is here. Then slightly closer to the solution. Then again, that we make the slope. Maybe this is almost the slope is 0, so it's a little bit problem. But we continue this procedure to approach to some solution, some root of f of x. So we have to update this. So maybe this is x old, then this is x new. Then we continue this procedure again and again until f of x value is not more than 0.001 in absolute value. Then if the f of x is within 0.001, then we report this x as an approximate solution. Yeah, so no guarantee that it converges. And yeah, like this case, it's if derivative is 0 or something, then sometimes it diverges. But if we are lucky, then we can find we can find an approximate solution. So the question A is develop an R function described by this algorithm, and the input is function f, and output is the root. Okay, so input is only f, so no other input. So you have to calculate the numerical derivative within the function. You have to update the x value within the function, and you have to judge the size of f of x within the function. Then finally, the report x, so that the input is just f. And B is just the try this function, your function, with some examples. The one is this. Obviously, the root is x is equal to the fifth root of 0.5, right? And I don't know, you can calculate it, but so you can check it. And the g of x, I think this is a little more complicated, the sine curve. So you can just start with x is equal to 1/2 and find the solution. Yeah, so that's the question. And I got another question from a student for number 3, part D. Should we only get 1% as the result after bootstrapping? You will get 1,000 percentages as the result after bootstrapping, because one bootstrap iteration it gives 1%, right? 90 over 300 or 108 over 300. So we will have 1,000 percentages. Then we can make a distribution. Do you have any other questions? In question 4, basically, we have to develop a functional because the input is function. So just I gave the one example of our function, whose input is a function. So this is actually, I make this function eval 10 function. So if we put function g, then we evaluate this function at x is equal to 10. So that is this function. So if g is the function x squared plus 2x, and we put this g in eval 10 function, then we evaluate this g at 10. So 10 squared plus 2 times 10 is 120. So it returns 120. So this eval function, eval 10 function, the input is function, then output is the g of 10. So this isn't really related to this question 4, but the question 4 also asks you to develop a function whose input is a function. So just that's why I put this example here. Can we, I got another question. Can we enforce types on the parameters of our functions? Types on the parameters of our function. Sorry, what do you mean? Data types like numeric or function or string? Uh, not sure what do you mean. So that you consider a character valued function or something? So this is just the numeric case. So you can assume that input is a function. Function's output is always numeric. So okay, I got another comment. Like in C++, you have to specify your parameters are an integer or a string. Yeah, so R does not have to, in R, we don't have to specify what class the function takes. So uh, uh, sorry, I cannot answer a question well, but you can, yeah, you can assume the function. The function is just okay. So the domain of the function is just some maybe all continuous numbers. Yeah. So suppose that the function has domain of entire real numbers. Yeah, just we assume the continuous function with the domain from negative infinity to positive infinity. Yeah. Okay. So other questions? Okay, so we continue chapter 6. So since maybe the last Monday, no, last Tuesday we started linear regression. So linear regression is again like this. What's that? Yeah, so maybe. So linear regression is like this. So we have basically X and Y. So we only have one univariate x. So we want to explain y by x. So y is equal to a plus bx plus epsilon. And we learned how to determine a and b. We have some formulas. And we determine this function, this line, so that the sum of squared residuals is minimized. So this quantity is minimized. So we find the such a and b. And this function is actually the function of a and b, quadratic function of a and b. So if we take the derivative of this, this becomes a linear equation of a and b. So it's not too difficult to find a and b. And we have some formula, but it's more convenient to use matrix form. So remember that we have the matrix form of this linear regression. So we define y as this, x as this, and beta as this, and epsilon as this. We have n observations. So we make a vector of n elements. Then we write everything by matrix form. Then beta hat, basically the estimate of a hat and b hat, that is given by this one. So actually the proof of this x prime x inverse x prime y, x prime is the x transpose. The proof is pretty simple, and we have done that before. And also, we have formula for variance of beta hat. So beta hat is a hat and b hat. And this depends on our observations. If we have 10 observations, a and b, the true value of a and b are not observable, but we can just estimate a hat and b hat. If we have another set of 10 observations, our a hat and b hat may be different. So in such a case, we have different a hat and b hat. So a hat and b hat have some variability, and that is given by this formula. Variance of b hat is equal to this. And to be exact, variance of b hat means the variance of a hat and variance of b hat on the diagonal term, and the off diagonal term that we have the covariance of a hat b hat. So this number and this number should be the same. So we have estimated a and b, and we have estimated the variability and a and b. And also we studied how this estimate is distributed. So if we have true value of a, that is a naught, for example, then a hat minus a naught over standard error of a hat, that is calculated by variance of a hat. So that follows t distribution with degrees of freedom n minus 2. So that is true for both a and b. Okay, and today's topic is prediction. So based on the model, if we observe a new observation, how to estimate the y? So our assumption is we estimate a hat and b hat based on these n observations. And suppose that we have new observation, but we only know x value. Then how to estimate y naught? And the natural thinking is if we know a hat and b hat, then you can just plug in x naught. That is our estimate, the y naught. So that isn't really too difficult. It's just a plug-in number. But the but the problem is how reliable this estimate is. So that is today's main topic. And here the x naught is the red version of x naught is a vector of 1 and x naught. So basically we have a and b. So we have to calculate this. So we have to calculate a plus b times x naught. So that is the product of the two matrices, or the inner product of two vectors. So 1 x naught and ab. So this, so the x naught is the vector of 1 and x naught. Yeah, so it's a little confusing, but the x naught denotes this red x naught. So this denotes x naught denotes vector of 1 and x naught in the following pages. Okay, so at first, we want to see the confidence interval for y naught. Okay, so we have A and B, and we can construct the confidence interval for A and confidence interval for B because we know that the A minus A naught over standard, maybe. Yeah. So this follows T distribution with degrees of freedom n minus 2. So we can construct confidence interval for the true value of A naught, A and B. But our interest is, y hat. Y hat is equal to A plus B times X naught. So we want to calculate the confidence interval for this quantity, not just A, not just B. We want to calculate confidence interval for A plus B times X naught. So what's that? So that is given by this theorem. So variance of, so the y not hat. So that is equal to, A plus B times X naught. So that is given by actually this formula. So y hat naught is actually the X naught transpose times beta hat, right? So, and actually this is given by this. Why? I can give you some reason. So, so basically we have variance of beta hat, right? So variance of beta hat is given by sigma times X transpose X inverse. So X naught transpose times beta hat. The variance of this is also calculated using this. So variance of X naught beta hat. This is in general the X naught transpose times the variance of beta hat and the X naught transpose. So generally, if we have some vector, the vector comes here and the transpose of the vector comes here. So this becomes X naught transpose times sigma squared times X prime X inverse. The X naught transpose cancel. Sigma square is a constant. And X naught transpose. This is actually the 1 by 2 matrix. And then X prime X inverse is 2 by 2. And X naught is 2 by 1. So this is a scalar. So you can get this. And that is actually appear here. So this is the proof. And actually, if we consider y hat minus expectation of y naught hat divided by standard error of y naught hat, this follows the T distribution with degrees of freedom n minus 2. I did not prove it, but it's similar to the the t-test, similar to the theorem in t-test. So in t-test, we calculated and X bar minus mu naught divided by standard error of X bar. So this follows T distribution with df n minus 2. So with the same reason, you can calculate n minus 1 maybe. So with a similar reason, we can prove that this theorem, and based on this theorem, that we can calculate the confidence interval for this quantity expectation of y naught hat. So true, value, the true expected value of y naught. And the confidence interval is given by this quantity. So y naught hat plus minus the T distribution sub 1 minus alpha over 2. So that is basically, if we have T distribution, PDF, then if this area is 1 minus, sorry, this area is alpha over 2, this is T sub 1 minus alpha over 2. So this point. So using this quantile point, that we can say the confidence interval for the y naught hat, or expectation of y naught. This is the y naught plus minus the T sub 1 minus alpha over 2. Degrees of freedom is n minus 2 times square root of the variance. So variance is the above here. So square root of variance. And the sigma is the error size, and error size is estimated by the sum of squared errors divided by sum of squared residuals divided by n minus 2. So you can use S instead of sigma. Yeah, so in this way, we can calculate confidence interval. So we can see basically we can see the variability of A and B, but the basically expected value of Y0 depends on the reliability of this quantity depends on our estimate A hat and B hat. And that variability is evaluated by this formula. Any questions so far? This is a little complicated, but yeah, but always, if you use our language, you can make this formula into code, then you can calculate it. And that is confidence interval. What's the expected value of y naught? But even if we correctly identify y naught as a plus b times x naught plus epsilon naught, even if we know this correctly, still we have variability of epsilon naught. So this is a kind of intrinsic error. So even if we estimate the model and we know the true model, still the y naught has intrinsic error of epsilon naught. So expectation of y naught only depends on this term, but actual y naught also depends on this error. So if we consider the variability of y naught, then that is a little larger than variability of expectation of y naught. And how to evaluate that? Y naught is this one. And to estimate y naught, we have to use beta hat, A hat and B hat. But the variability of y naught also comes from epsilon naught, right? So we have to add basically two random variables to evaluate the variability of estimate of y naught. Yeah, we have to evaluate the variability of y naught. And the beta hat is calculated based on our observation x1 to xn, right? And epsilon naught, the variability of epsilon naught comes from x naught, y naught. So these are, our assumption is that these are independent observations. So that means these two quantities are independent. So variability of this entire quantity, the variability of y naught, is summation of these two quantities. And epsilon naught, so basically this should be equal to variance of x naught prime beta hat plus variance of epsilon naught. And variance of x prime naught beta hat, that is given by the previous page. This one times sigma. And the variance of epsilon naught is by definition sigma square. So we have 1 here. So 1 plus this quantity times sigma square. That is our prediction interval. So actually, how reliable the y naught is, how much variability y naught has. So the prediction interval. So what's the range for y naught? is given by this formula. So we have 1 here. Confidence interval is for expectation of y naught, and the prediction interval is for y naught itself. So which one should we use, confidence interval or prediction interval? So prediction interval shows the variability of y naught in usual sense. So actually, when we observe x naught, what's the distribution of y naught? Then we have to use prediction interval to see what's the actual range. And the confidence interval is for expectation of y naught. So the effect of the intrinsic error epsilon naught is not considered. So just we want to focus on the a plus b times x naught. We ignore epsilon naught. So that is the confidence interval. So often in statistics, our interest is to estimate parameters, not intrinsic errors. So in such a case, we have to use confidence interval. But in practical sense, the variability of y naught is described by prediction interval. Any questions? Yeah, so confidence interval and prediction intervals are different. And the next one is the confidence bands and prediction bands. So confidence bands corresponds to confidence interval. So confidence intervals for all possible x naught is a band. So it is called the confidence band. So that means if we have x-axis and we have y-axis, and for each given x value, we can calculate confidence interval like this. And another value, we have confidence interval here. And another value, confidence interval here. And here, confidence interval is here. And so on. So each x value, we can calculate the confidence interval. Then if we connect these confidence interval, then we can calculate the band. So usually band looks like this because if we have many observations around here, we can estimate the confidence interval pretty accurately. But if observations are almost out of the range of our sample, it's very hard to estimate how wide so it's hard to reliably estimate the expectation of y0. So it's wider. Okay. So confidence band is like this. And prediction band is the same thing. So the prediction interval for each possible x naught. Yeah. And yeah, often in practice, we make this confidence band and the prediction band based on our observations, x1, x2, x3, and so on. Because we have infinitely many possible x values, so we cannot calculate everything. So basically, we are estimating this band for range in which x exists. So it's reasonable that we take just the observed x values and we make a band, make interval for each of those x. Yeah, and both bands gets wider as x gets farther away from the center x bar. And here is an example. So this is the condominium data, square footage and the price of the condominium. Price is in $1,000. And these are observations, and the red one is confidence band. So that one is confidence interval, confidence band, I would say, the confidence band. CB, I don't know. So confidence interval is denoted by CI, the confidence band. And confidence band is for true value. So that means basically the line, the fitted line is within this band with 95% probability in this case. So fitted line changes a little bit if the observations, we take different sample. So the fitted line is like this or like this, and this red band that includes this fitted line with I don't sorry this dotted line includes the true fitted line with 95% probability. Yeah. So yeah, so it's slightly different from the statement that fitted line is within this interval with 95% probability, but rather we have the true true line, and this red band includes true line with 95% probability. So that's why this has like the shape of hyperbola, because if slope is slightly larger, then if x value is far away from center, then so this band gets like this. So yeah. So you can see that if we fluctuate the straight line, then depending on the discrepancy in slope and intercept, then the possible range that makes the area surrounded by hyperbola, you can imagine. And the green one is prediction interval. So this actually basically means how many observations in the future are within this band. So this has the sample size of 48 or something, and we have one observation, maybe two observations out of this range. So 2 out of 48 is about 4%. So this is about 5%. So about 95% of observations are within the band. Actually, this observation, it's not clear whether it's inside or outside. So we can see that 95% of observations are within this green range. So that is the meaning of prediction band. So confidence band for lines and the prediction band for actual observations. Any questions? Yeah, and this is the sample code for the previous figure. And this is some non-trivial feature, so I want to discuss it. And okay, so at first, yeah, just we set the x limit and y limit, and that's fine. And confidence band and prediction band, of course, we can calculate from scratch, but we can use actually a predict function of LM object and specify the interval is equal to C for confidence and P for prediction. So we can calculate this and CI and PI. So this calculate confidence interval for each observed X value, Xi. Okay. And this is prediction interval for each observed Xi. So I is equal to maybe 1 to 48 in this case. And I think that this is the trick we have to make confidence and prediction band. We order this. So basically, we order observations. We order observations by increasing order. Order observations x1 to x48. So usually the x parenthesis 1 represents the smallest observation. So smallest, second smallest, and third smallest, and so on. Then we make a plot. Actually, I use the matlines function. So this is, okay, so again, this is sorted square footage. So this is the sorted observations, x1 to x48. Then put the confidence interval for that. And just we overlay this for prediction interval as well. Then we put some legend. Then we become here. So why we have to order it? Because we have many intervals. So if we don't order it, then the order of observations are random. So that means that we randomly connect points on these bands. So for example, this lower band for confidence interval, we randomly connect 48 points like this and this. So maybe that means we connect this to this first. Sorry. We connect this to this, then this to this, then we go back to this, and we go back to this, and we go back to this. Then actually it does not become a band, but it's a kind of messy, the random line graph or something like that. So to make the beautiful band, that we have to order X values, and we connect it one by one. So just in order. So that's why that we order this to make bands. So these are exercises to do that. And actually exercise 3 that asks you to calculate how to calculate prediction band and the confidence band by hand using formulas. Okay, and I don't know. Do you want to do practice, or you want me to continue to the next one? Anyway, I have to make a survey, but anyone, any opinion? Well, I think I got one question. So can you show us what the output of the predict function looks like in R? Yeah, so predict function has returns some matrix, and the matrix includes the several columns. The one column is the lower bound of the confidence band, and the one is upper bound, and maybe possibly the fitted value as well. So I think probably three columns. Yeah. Maybe you want to show me? Okay. So yeah, so okay, so this is our window. Maybe we create some X. So X is maybe a random number of maybe, okay, 50 observations. And Y is, we define Y as maybe, okay, so 2 plus 0.5, 4 times maybe X plus maybe R norm of maybe 50. Yeah. Then maybe plot XY. Then I think this is too random. So maybe we change the standard deviation to 0.5, then plot Y. Then we get the X and Y. Maybe somewhat, maybe we want to make it a little smaller. XY. Okay, so like this. Okay, and we want to make a straight line, and they want to fit the predictor. So, okay, so LM. This is LM, and Y over X. Okay. Then predict and LM, and the int is equal to C. Then this. So we have the 3 columns of numbers, and the first column is fitted value. Second column is lower bound, and the third one is upper bound. Yeah. Okay, I think it's good place to stop. So I will stop here, and I would like you to do exercise. We have several exercises, but we have 20 minutes, so maybe you can try a harder one. Yeah, exercise 2 and 3 are in the yeah. So iris data is available in default R package. So you regress the sepal length on sepal width. So sepal length is Y and sepal width is X. And for first 50 observations, original dataset include 150 observations and create a plot with regression line and the confidence interval and the prediction bands. And if you have done this, then you can do exercise 3. That is manually doing exercise 2. Sorry, I got another question. For number 3, part D, this is probably midterm. Should we only get 1% as, I think this, sorry, no. What does int C means? So that is in slide. Int C is confidence interval. Int P is the prediction interval. Okay, so I will set up, okay, so at first, maybe I have to check the attendance. Participants, we check attendance here. And we have 18 students. Okay, and I will set up the maybe 4 breakout rooms to do exercise 2 and exercise 3. And for maybe 15 minutes, maybe a little, yeah. And 1, 2, 3, 4, 5, maybe we move 1 person to room 2, 4, 4, 5, 4. Yes, okay. So about 15 minutes. Exercise 2 and 3.
Professor? You are muted.
Sorry, I don't know why other people. Oh, I think I didn't close the room. Sorry.
No, you didn't close the room. I left because it's 7:47.
Yeah. Sorry. Yeah, sorry about that. Yeah, I thought I closed the room, but I did not. Okay, so I think I don't have enough time to explain the solution, so I will upload the solution. But I got the questions from 2 rooms about the AB line function. And actually, AB line works in under some conditions and does not work in under some conditions. And okay, so this is my code. At first, I make a plot by using this one. Then after that, I attach this and I put AB line. And it did not work. But when I plot just the sepal length and sepal width after attaching this one, and after that, immediately after that, I put the AB line of sepal width and sepal length, then it worked. So probably there's some restrictions on how to, put this X and Y and X. So if these are exactly the same object, then it works. But if these are specified slightly different ways, then probably it does not work. Okay. But anyway, so that's it for today, and I will upload the question for exercise 2. Okay, so see you on Tuesday next week if you don't have any questions. See you.
Have a nice night.